What I'm going to talk about here in this video is I'm going to talk about non-homogeneous second-order linear differential equations. Now, in order to do these, we first have to understand what a non-homogeneous second-order differential equation is, how they differ from homogeneous ones, and then how we can approach solving them in the manner that allows us to get an accurate solution, whether it be a general solution or a particular solution for our system. Now we know differential equations, second-order differential equations, come in the form a d2y by dx squared plus b dy by dx plus cy equals q of x. So these are our second-order differential equations. Now if q of x is equal to 0, this is what's called homogeneous. If q of x does not equal to 0 and it's got some functional form, this equation is then called non-homogeneous, or you see it sometimes written as inhomogeneous. Now we have to be able to solve these. But in order to solve these, we have to also take it as a part homogeneous and a part of a particular functional type in order to get the full solution. Now the solutions for this are embedded in some theory that we're going to talk about just now. Now we know what form non-homogeneous equations take. Let's imagine that I'm going to give you a particular solution, g of x. Now this function g of x solves the equation, so what we know is that a d2g by dx squared plus b dg by dx plus cg equals q of x. Yeah, so whatever function of g that we've picked, it satisfies that. Now let's imagine that we take g of x plus k of x as another particular solution. So this combination of these two functions is also a particular solution. What that then means is if we substitute them into the form of our equation, we get a d2 of g plus k by dx squared plus b of d of g plus k by dx plus c bracket g plus k, and that equals q of x. What I can then do is separate these out into their specific terms involving just the g's and k's. So what I can then say is fine, so that lets me say a d2g by dx squared plus a d2k by dx squared plus b dg by dx plus b dk by dx plus cg plus ck equals q of x. Now if I look through this and I start to gather terms together, I've got a d2g by dx squared plus b dg by dx plus cg. So if I stick that together, I get a d2g by dx squared plus b dg by dx plus cg, and I can then group the k's together as well, and I'll get plus a d2k by dx squared plus b dk by dx plus ck equals q of x. So now that I've got that, what I can do is notice that this comes from this first part here, where what I've told you is that that is a particular solution to that equation. So I know g of x satisfies that equation, which means all of this here is the equivalent of q of x. So I'm then able to say, it's fine, what that means is that a d2k by dx squared plus b dk by dx plus ck plus q of x, coming from this part here, equals the q of x on this side. If I then shift the q of x across, what I'll end up getting is that a d2k by dx squared plus b dk by dx plus ck is equal to 0. So what I'm showing you here is that if I have two functions, both of which give me a solution to that equation, I've got one that satisfies the equation on the right hand side, so it takes into account what that is. I've also got a part of it that satisfies the homogeneous style of the equation. So I've got two functions combined together to give me the total solution if I've got an inhomogeneous equation. So what that means is that the solution for this takes that format. It takes the format of g of x plus k of x. Now in this, what we'll say is that g of x is called the particular integral, and this is the solution of the homogeneous equation. K of x in this case is what's called a complementary function. And what we need is this to get the full solution of the non-homogeneous equation, because what that does is that takes into account the fact that I've got a solution on the right hand side. So I've got a relationship q of x, which needs to be taken into account as part of my overall solution. Now the overall set of steps to solve these follows the same route. The big part that causes a change is whatever the form of q of x is, because the complementary function depends upon that. So for example, if my complementary function is an exponential, I can't have if my q of x is an exponential, I can't have a complementary function that's a quadratic. It just wouldn't work. So we have to take that into account. Now, we've got to ask ourselves how we pick the form of our particular integral. Well, we pick it based upon what q of x is. So if q of x is a linear function, i.e. 2x, the particular integral we pick is y equals ax plus b. If it's an exponential, so 2e to the mx, we'd pick y equal to ae to the mx. A quadratic, we'd pick y equals ax squared plus bx plus c. And a trig function, we'd set y equal to a sine x plus b cos x. Now, key point to note there is I've included both trig functions, even if only one of them appears in the q of x. There are a few special cases that can arise dependent upon the complementary function itself, because remember we've got the three forms of our complementary function that occur. Now let's say our complementary function is something along the lines of a plus b e to the ax. What we'll do is if q of x is a linear function, we pick a particular integral to be x cx plus d, because what that means is that takes into account I've got a linear part of my complementary function as well as an exponential, and I'm still going to get all the terms required for my particular integral to cover q of x. If the complementary function takes the form y e to the ax plus bx e to the ax, and our q of x is the form c e to the ax, what we're going to do is actually make it dx squared e to the ax. Because if I don't, and I have it in the same exponential format as the others, what's going to happen is it's going to get enveloped in the complementary function, and that term to try and satisfy the q of x on the right hand side is no longer going to exist. So what we do is we take that into account and ensure we have that term occurring by multiplying by the x squared there. Now again for this one here, if I have a complementary function in the format of a trig one where I've got a sine bx plus b cos bx, and I take a q of x being of the form of d sine bx or it's e sine bx, something along those lines, what I'll do is in order to ensure that my sines or my cosines are not enveloped again by the sine or the cosine, take my particular integral to be the e sine bx plus f cos dx as we did before, but multiply the whole thing by the x. That will keep that as part of our function, and it will then give us a part of the solution relating to our q of x. So bits to think about when it's there. Essentially what you want is you want the complementary function to be one part, your particular integral to be another part, and neither of the two of them to envelop each other and become part of one function. So no same parts go together. We need solutions to both to combine to give us an overall solution. Now when we're solving a question like this, there's 5 steps that we really should follow. First one is we have to find our complementary function. We get that by setting q of x equal to 0 and solve it as a homogeneous equation. Second thing we then have to do is choose a particular integral which is of the format of q of x. Now it's got generic coefficients as I've mentioned previously. So for example, a linear one is ax plus b. We then calculate derivatives of this and substitute into the full equation. We then simplify this and equate both sides and this will help me find my coefficients. The q of x on the right will have its coefficients in, it will have actual numerical values. The equation on the left won't. It'll have arbitrary coefficients. So this allows me to then find these. What we then do is we write our final solution in the format y equals g of x plus h of x. So g of x is a complementary function, h of x is a particular integral. Now in this you'll note that your complementary function will still have arbitrary constants in it. Now, if you're given initial conditions for the first derivative and for y, we can use these to find the coefficients. This is what's called the particular solution. If we're asked for the general solution, we will still have those arbitrary constants in play, and we will still have the a and the b there. Now, it's a fairly easy set of steps to follow. I'm not going to put any examples here for you because what I want to do is I'm going to do several videos to follow this with different examples of different formats that we can choose of a particular integral. Have a look at these and make sure you understand how to follow the set of steps through in our approach to solving these inhomogeneous equations.